Okay, so in this, we're going to take a look at, we've been talking about Taylor series, Taylor polynomials. Now we're going to look at Taylor's theorem. All right, now the theorem we can think of, or it's defined as this, right? So the remainder in our approximation using the nth polynomial is Rn equals the difference between the actual function value and the nth polynomial, right? Now here is a visualization of that, right? So here you see the line, right, being the polynomial, and then the curve itself, right, f of x is the sine curve here, right? And then this line that you see from the curve to the polynomial, that's the remainder, right? The gap in the two, right? And then as we see here, right, the higher the polynomial is used, right, the less that gap is, right? The remainder becomes less, right? Depending, again, the remainder, again, the further out you get from where you're centering at, right, the approximation becomes less reliable, right? As we can see from the remainder growing, right? But that's exactly what this, what this equation is telling you, right? The nth remainder can be classified by the difference in the function value and the function value, or whatever the x value that we're using to approximate using the nth polynomial. Okay, so the idea here behind the remainder theorem is, if we think of R0 is really just, it's f of x minus p0 of x. Right, now the the zeroth Taylor polynomial is just the function value at a. Excuse me here. All right, now what we can do, I'm sorry, it should be, what we can do here is use a theorem from Math 1, the mean value theorem, right? MVT states that there exists, if f is continuous, right, there exists some value between x and a where this equation holds. Oops. All right, and kind of using this equation, multiplying both sides by x minus a, we have the zero derivative, or excuse me, the remainder of r sub 0 to be equal to this value of c, x minus a. All right, that value of c is just a number between x and a. Usually we won't be able to find, right? But we will. What we want to do is we want to bound it, right? And we'll get into more of how to do that, right? But more in general, using this same type of argument with the mean value theorem, we can generalize the argument. Now, we won't go through the details of that. We'll just take the result here to be r to the n of x is equal to f to the n plus 1. Notice that the derivative is 1 higher of that value c over n plus 1 factorial, and then x minus a to the n plus 1, where again c is just some value in the interval x and a. Okay, all right, so what we're going to do here is that we're going to find a way. We want to bound, since this value is some finite value, so we want a way to bound the remainder, right? In other words, we want an upper bound for the error, right? It tells me that the error can be at most this much. All right, so we'll use m over m plus 1 factorial, absolute value of x minus a. So we're looking for the absolute error, right? I don't really care whether it's above or below. And this is Taylor's theorem with remainder, right? Essentially what we have here. Let f be a function, so we can differentiate n plus 1 times on an interval I containing the real number a. Let p sub n be the nth Taylor polynomial, so we've established this equation, right, the remainder. And then for each x in the interval, the remainder is equal to this equation here, Right now, if there exists a real number n such that this is true, right? So we bound the nth derivative by some value m. Right, then if I can bound the derivative, essentially what it comes down to is if you can bound the n plus 1 derivative, you can bound the remainder, right? It gives you an utmost bound as to how large the error can be. Okay, so let's take a look at an example of a problem that we might be asked to solve here. So for this example here, I want to find the first and second Taylor polynomials for f of x equals to root x at x is equal to 4, and then use these polynomials to estimate square root of 6, right? And then use Taylor's theorem to bound the error. Okay, so here let's start by building the polynomials. We're going to need, so f of x, f prime of x, and f double prime of x. And actually, using the error, we're also going to need f triple prime of x, right? Because the r sub 2, right, is going to require us to have the third derivative. So we'll just do it right here. Okay, so our function is square root of x. The first derivative is 1 over 2 x to the 1/2, or 1/2 x to the negative 1/2. All right, the second derivative will be negative 1/4 x to the negative 3/2. All right, and then our third derivative, one more time, 3 over 8 x to the negative 5/2. All right, and then at 4, right, that's where we're centering it at. F of 4 is root 4, which is 2. F prime of 4 is 1/4, right? F double prime of 4, right, that's 1/4 times 1 over 4 to the 3/2, and negative. All right, 4 to the 3/2, right? The way you want to do that is, right, the denominator is the root, so root of 4 is 2, 2 to the third is 8, 8 times 4 is 32. All right, and then f triple prime of 4 as well, right? That's going to be 3/8 times 1 over 4 to the 5/2, and the same logic here, right? Square root of 4 is 2, and then 2 to the 5th is 32. All right, and then 32 times 8 gives me 256, so 3 over 256, right, positive. Okay, so now we have these function values, so now let's begin with building our Taylor polynomials, right? Our P1 of x is going to be f of 4 plus f prime of 4 times x minus 4, right? So plugging those values in, we get 2 plus 1/4 x minus 4. Our second polynomial here is going to be f of 4 plus f prime of 4, so essentially P1, right? And then we add to that f double prime of 4 x minus 4 squared, right? So that gives me 2 plus 1/4 x minus 4 minus 1 over 32 x minus 4 squared. All right, so now we have our two Taylor polynomials. And the next part of this question asks me to approximate root 6. So the way that works is we now have our polynomial. So I'm going to have two approximations. The first one is going to be using P1 of 6. So you plug in 6 into our first polynomial here. So that equals 2 plus 1/4, 6 minus 4. And that equals to 2.5. All right, now our second approximation, root 6, approximately P2 of 6. So that's 2 plus 1/4, 6 minus 4, minus 1/32, 6 minus 4 squared, which is equal to 2.375. Okay, all right, so now we have both of these approximations, and here, switching over here, we have our graph, right? Here I just generalized it a f of a, right? So we have our root function here in red. All right, okay, and then the center is at 4, and I'm asked to, right, look at the values here, right, where the blue one is our first polynomial, and the black one is our second Taylor polynomial, right? So looking at this here, we see that from the graph, the true value is somewhere in between, right? That's the red here of the function here. Okay, so now the next thing I was asked to do is to bound the error. All right. So the way we do that, we're going to use Taylor's theorem, right? So here, I know that the remainder of 6 is, excuse me, is equal to f double prime of some value c over 2 factorial 6 minus 4 squared. Now here, in order to make sure to account that I want to capture what is the largest error that can be, I want to find the largest value. So c is going to live somewhere in between 4 and 6, right? Actually inclusive, it could be the endpoints, somewhere in there. All right, so if I take a look here, at f double prime of x, we get negative 1 over 4 x to the 3/2, right? And since I want to bound my absolute error, I really want to look at just the positive values here. Now looking at this function, x to the 3/2 is increasing on 4 to 6. All right, x to the 3/2 is increasing on 4 to 6. So if it's getting bigger, 1 over a bigger number is getting smaller, right? The actual fraction itself, again, we're ignoring the sign since we're taking the absolute, it is decreasing from 4 to 6. All right, so what we use here is the error can be bounded by f double prime of 4 over 2 factorial, and then this is just 6 minus 4, which is 2 squared. All right. And we saw that f double prime of 4 is 1/32. So here, simplifying this, we get 2 squared over 32 times 2 factorial. All right. Okay, and here, just calculating this here, so that becomes, the error is at most 0.0625. All right, and in the similar fashion, R2 of 6, right, the we can bound it. It's going to be less than or equal to the largest value for our third derivative. Occurs at 4, right, over 3 factorial. And that becomes 6 minus 4 cubed. So that becomes, we saw that was 3 over 256. That was our f triple prime at 4, right? And then we have times 3 factorial, and then this is 2 to the third power. All right, so typing all that in, right? Okay, and then this is 0.015625. Okay, so we see that the error becomes less, right, compared to our first and our second Taylor polynomial. Okay, so now we have an error in our approximation. All right, now to wrap this section up here is, well, this Taylor series that the infinite series, right, not so much the Taylor polynomials, do they actually represent the function, right? Now, here in our theorem here, last theorem in this section here, it says that the convergence of the Taylor series. So we suppose that f has derivatives of all orders on interval I containing a. Then the Taylor series, which is defined here, converges to f of x for all x in I if and only if the remainder as n goes to infinity of r sub n of x goes to 0. All right, so then it does converge, right? Wherever the interval of convergence is, then that's where the Taylor series converges to so it represents the actual function, right? It's equal to those function values. So for example here, right, previously we have shown that so in this example we want to prove that e to the x is equal, to the sum of its Maclaurin series. So previously we've shown that e to the x is this Taylor series here. Okay, with interval of convergence to be negative infinity to infinity. But up to now we said that the Taylor is an approximation here of this, but here we want to show is if we look at the remainder theorem, right? So r sub n. So we want to take a look at the remainder is, right, some value m, right, over m plus 1 factorial x minus a to the m plus 1. All right. Okay, so now I know that for any derivative of my function, here in this case f of x is e to the x, so I know the nth derivative is always e to the x, right? Simple, right? And let's say that I assume that the absolute value of x is less than or equal to some value d. All right. Now, due to the one-to-one nature, d is just some constant, right? Whatever x is, right, then x is less than some value d. All right. We don't really need to find it. We just know that it exists, right? So, and this is how we find it, right? It's just any value, right, that is less than or bigger than x. Okay, some finite value. So that means that the absolute value due to the one-to-one nature of the exponential is if this is true, that the absolute value of x has to be less than d, then the exponential is less than e to the d, less than or equal to. Okay? All right. So now that is going to help us bound our error, right? The absolute value of r to the n of x, right, is less than or equal to e to the d. I'll have this be my value m, right, over n plus 1 factorial. And since it's Maclaurin, my a is 0, so x to the n plus 1, right? Okay. Okay, so now I want to take a look at the limit as n goes to infinity of r sub n of x, which is equal to e to the d, does not depend on n, so I'll take it out of the limit, right, which is nice, right? It doesn't depend on n. One of the reasons why I want to bound it n, it doesn't depend on the value of x, right? It just knows whenever I choose an x, I have a way that d is just some value that is bigger than that x. Infinity of absolute value of x to the n plus 1 over n plus 1 factorial. Right, now in a previous section we looked at the order of functions of order of increase, right? So for something like this, we saw the factorial increases faster than this exponent of n plus 1. So here, this whole limit is going to 0, right? So we're using the fact here that the limit as n goes to infinity of x to the n over n factorial is in fact 0. All right, so that goes to 0 times e to the d again just goes to 0. All right, so that proves that, therefore, that the exponential is the same equivalent across the whole interval of convergence, which is from negative infinity to infinity, is equal to this function. Right, so these are one and the same thing. They represent the exact same thing, right? Now, more importantly is that if we let x be 1, I have a representation of an irrational number e, right, using rational numbers, right? It just happens to be an infinite series, right? So e can be actually represented like this, right? 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, etc. Right, by setting x equal to 1. So now I have an expression for the irrational number e, right, using a infinite sum. Right.